this problem here says that we have an equilibrium equation. There it is. And at equilibrium, very important, I'm going to highlight that. At equilibrium, we have these guys to have these concentrations. So we're going to be able to calculate the Kc because we have equilibrium concentration. Jess? Okay. That equilibrium word is huge for us today because we're going to learn when sometimes it doesn't say that, then it's a question for us. All right. First of all, I'm hoping everybody's really good on this by now. Kc expression is going to be concentration of CO2 raised to the first power times concentration of H2 raised to the first power over concentration of CO raised to the first power over concentration of H2O raised to the first power. The Kp looks very similar to that except no brackets, yes? You must use capital P. Now, you don't have to use parentheses, so I'm going to do it the first time without parentheses. You can do it basically just like this and not have parentheses because they don't have any power, so they don't really have to have parentheses. If you are more comfortable, as I am, putting parentheses in, you can do that. Comfortable with Kp and Kc expressions? Okay. So now we're ready to go calculate the value of the Kc, so we're going to say equals, and we're just going to plug in our numbers. 0.012 molarity times 0.012 molarity divided by 0.01 molarity, the CO value, and the H2O value, 0.02 molarity. And we're going to get a value out that's equal to 0.72. Okay, so the Kc is equal to 0.72. 72, Ms. Matney. All right, Kyle, talk to me. What does a Kc, being a number less than 1, say to you? It's not TPF. Jordan, what else does it say to you? Positive delta G. Hayden, what else does it say to you?
Negative E cell.
Negative E cell. Austin, what else does it say to you? Not spontaneous. Matt, what else does it say to you? Oh, it's not a galvanic cell. Awesome. Okay. Now, to get the Kp, you technically are going to have to do pressure is equal to molarity times R times T twice because you need the P's to be able to plug in. Yes? All right. So we're going to say pressure is equal to 0.012 molarity times R, 0.0821, times an understood temperature, if they don't give you one, of 298. All right, Kyle, what did that pressure come out to be? Okay, atmospheres. And then the other one of these that we're going to do is pressure is equal to 0.01 molar times R times T, 298, and Matthew, what did you get for that pressure? 0.294 atmospheres. That's for the CO2. What about 0.01 plugged in? What did you get for that value? 0.245. It's got to be a little less because less molarity would give me that. All right. And then if that's the pressure of, let's write it in, the pressure of the CO, the pressure of the H2O, Kelsey, how is that going to compare to that pressure? How is the pressure of H2O going to compare to the pressure of the CO? It's going to be doubled. So I just say 2 times 2.245, and that is a point. Y'all just didn't see the point. 0.245 atmospheres, yes? All right. Now, Nyree, how do I get a Kp value? How do I get a Kp value from all those pressures? I get total pressure if I add them, yes, but how do I get a Kp value? Products over reactants. I plug them in and I do division. So I'll take the 0.294 atmospheres times 0.294 atmospheres divided by the 0.245 atmospheres, divided also by the 2 times 0.245 atmospheres. And it's going to give me, Austin, a KP that's also equal to what? .72. All right, so here's the question. Why are the KP and the KC values the same, Brianna? Because they all have coefficients of 1, and there's no change in the number of moles of gas from one side to the other. That means you can't predict the sign of delta S. And if you can't predict the sign of delta S, then KP and KC are the same Matthew values. You asked that question. Earlier, the question was asked, if KP and KC are the same values, same numbers, does that mean anything? Yes. It means that there's no change in the number of moles of gas from the reactant side to the product side. All right, next question. All right, this question. Who does not get invited to the KEQ party? Okay, so when you are asked here to write the KP expression first so you can plug and chug, all you're going to have is the pressure of ammonia times the pressure of the CO2. So all I'm going to do in this particular problem, since it says, let's grab a highlighter real quick, when equilibrium is reached, these are my partial pressures, then I can simply plug and chug and say 0.0773 atmospheres squared times 0.0387 atmospheres to the first. This is just a plug and chug question. It's just like the one before, but it's all KP. And you've got to keep in mind that on the OWL, what do you have to put on the bottom? Whoever has done the OWL at this point, at least started it, you have to put a 1. If there's no bottom, you got to put a 1. If there's no top, you got to put a 1 on the OWL. Don't have to do that for the bottom for me, but you do for the OWL. All right, last little piece here, and then we're done with this question, is total pressure is going to be equal to the pressure of the NH3 plus the pressure of the CO2. Is that a regular chemistry concept right there? Yes, it is. So all I'm doing is taking my two pressures of 0.0773 and 0.0387, and I'm just adding them together. That is an addition sign. And I get 0.116 atmospheres to be my total pressure for these gases.